So when drawing this one, right, make sure first draw the n equals 1, then draw the n equals infinity. So when drawing the n equals 2, it should be a bit higher than the midpoint of the n equals 1 and infinity. If they have asked you to draw the hydrogen spectrum, just draw only this one. Just draw only this one, right? Just draw only this one. If they have asked you to draw the hydrogen spectrum, only this is required, right? If they have asked you to draw the energy level diagram of the hydrogen atom, right? Energy level diagram of the hydrogen atom, then you need to draw this diagram. Is actually due to this. Actually, this line is due to the B transition, right? What you clearly see here is actually, right? Some electrons are appearing here 2 for excited hydrogen atoms. Some electrons are appearing at the n equals 3, third energy level. Some electrons are appearing at the n equals 4. That thing will happen with the excited hydrogen population. That is why we need to consider all these energy levels of the hydrogen atom. But when it comes to alone one ground state hydrogen atom, the electron is at the n equals 1, so no need to consider any other energy levels. The hydrogen spectrum is observed not by a single hydrogen atom. Remember that. That is very important to note that. The hydrogen spectrum is observed not from a single hydrogen atom. Actually, you can't isolate a single hydrogen atom. How can? How could it be possible to isolate one single hydrogen atom? The last line of the Lyman series gives you that is actually the highest energy line of the Lyman series. That will give you the ionization energy. If you know the frequency here, if you know the frequency of the last energy line of the Lyman series, you can apply the E is equal to h mu. That will give you the energy of the photon corresponds to that last line. That will be your ionization energy. Hello, good evening, Lamai. Right, let's start the class for today. Right, actually last day we have discussed about. Actually, we have started the discussion about the hydrogen spectrum. Right, this is what we have learned last day, just for a beginning. Right, so. Last day we were discussing about the hydrogen spectrum, right, and we have started the discussion, right, and we have discussed about few series of lines with the hydrogen spectrum, right, Lyman, Balmer, Paschen, Brackett and Fun, right. I have drawn only 3 here, right. Today we are going to discuss about the origins of the spectrum, right, how Bohr described the origin of the spectrum. That is our discussion today. Right, before going to that, right, let's discuss a bit about the last day's stuff, right, we have learned, right, because it will be very important to answer the questions coming from this section, right. So, this is the hydrogen spectrum, right. So, when it comes to this spectrum, right, there are few special observations are there, special patterns are appearing here, right. Let's discuss a bit about those things, right, before going to discussion of the origins of the spectrum, right. So, it's like this. Lamai, basically, if you are to consider a series of lines, of this spectrum, right? Let's consider the Lyman series of lines. So you see, right, going towards the higher frequency region, or may say higher energy region. The frequency high means the energy is also high, right? Frequency means also the energy, right? Energy or the frequency both are same because E is equal to h mu no. So E is proportional to mu no, as h is kind of a constant, right? So when going towards the higher energy region or when going towards the higher frequency region, you can clearly see the lines become closer to each other. Means the gaps between lines get smaller. Gaps between lines decreased when going towards the higher energy region or the higher frequency region in a considering series of lines. Even with the Balmer, the same thing appears. You clearly see gaps between the lines, right? Gaps between the lines decreases going towards the higher frequency or the higher energy region, even with the Paschen series. You clearly see that, right? So that is the first thing to observe here, the first pattern to observe with the series of lines in the Lyman series, right? So, sorry, in the hydrogen spectrum, sorry, right? So that is the first thing, right? Then the second stuff we have learned last day. Actually, the gap between the gap separating spectral series, the gaps separating the spectral series actually, right, increases. Gap separating the spectral series increases going towards the higher frequency region, right? Going towards the higher frequency region, gaps separating the spectral series get increased, right? That is another thing to observe here, right? So clearly get the concept. Gaps between spectral lines of a given series decreases. Gaps between spectral lines of a given series decreases going to the higher frequency region, but the gaps separating the spectral series, right? Gaps separating the series, right? Gaps separating the spectral series, right? The gaps separating the spectral series, these guys. That gaps separating the spectral series increases going towards the higher frequency region. Two opposite things, right? Clearly note that, right? Those are few things, right? The next pattern observed with this spectrum is actually, if you are to take the second line and onwards, from the Lyman series, right? If you are to copy paste that stuff at a lower frequency region, you get the Balmer series. If you are to take the second line onwards, this section from the Lyman series, and if you are to copy paste that stuff at the lower frequency region, you get the Balmer series. If you are to take the third line onwards from the Lyman series, and if you are to copy paste that stuff at further lower the frequency region, you get the Paschen series, right? That means the gaps between the second and third lines is actually the gap between the first and two lines of the Balmer series. Gap between the second and third line of the Lyman is actually the gap between the first and second line of the Balmer series. That is what we meant by the copy pasting. Just copy paste the stuff from second line onwards from the Lyman to here, you get the Balmer series. Just copy paste the stuff from third line onwards from Lyman, right, and paste it here, you get the Paschen series, right? That pattern is also observed with the spectrum, right? Those are the main 3 points together, right, with this spectral series, right, the hydrogen spectrum, right? Okay, so this is all about the hydrogen spectrum. When we are to written this thing, taking the higher frequency region as this, right, towards this section, towards left, the frequency is increasing, right? If they have asked you to draw the hydrogen spectrum, the same hydrogen spectrum, right? If they have asked you to draw the same hydrogen spectrum, but if they have changed the direction of increasing frequency, like this, can you draw the spectrum? Right? If frequency increases towards this section, can you draw the series, right? So that is some knowledge. There should be some knowledge you should have to draw the series towards this direction as well, right? Can we try? Let's try to draw the same hydrogen spectrum taking this direction as the frequency increasing region. Let's try to draw. So how to draw this one? It is like this, Laman. So basically, when you are supposed to draw the hydrogen spectrum, right, taking this direction as the frequency increasing region, right? First mark the regions. Where the spectral series appearing, right? So basically, higher frequency means this should be the UV region. The highest frequency comes up with UV region when considering the UV, IR, and the visible, right? And UV region is there. Then here you have the visible region, and here you have the IR region. This is actually considering the side of frequency increasing, frequency is highest at this region, that means the energy is highest at this region, so that should have, be the UV region, and frequency is lowest at this region, that means it should be the IR region, right? First mark the 3 regions like that, then mark the spectral series appearing with those regions. With the UV region, it is the Lyman, Lyman, right? With the visible region, it is the Balmer. First label the 3 series of lines, right? So then the Paschen here. This is how we are supposed to draw the hydrogen spectrum if the frequency is given as increasing towards the right? Okay, Lyman, Balmer, Paschen. When writing these things, make sure the gap here between Lyman and Balmer is high than the gap here at the between the Balmer and Paschen. This will be a lower value. The gap between the Lyman and Balmer should be a higher value than the gap between Balmer and Paschen. See? Why? Why is that? Because going towards the higher frequency region, the gap separating the spectral series should increase. Going towards higher frequency region. That point is very important, right? Considering that, just take like that, right? The Lyman and Balmer should have a greater gap, and Balmer and Paschen should have a smaller gap, right? Okay, then start drawing. Start drawing the spectral lines. Here, right? Okay, the first line of the Lyman. Always start with drawing the first line of the Lyman series. Basically, Lamai, the first line means for any given series, the first line means the lowest energy line. Of any given series, right? So Lyman's first line. So Lyman's first line we can draw from here, right? The Lyman's first line, when this Lyman series appears like this, right? So Lyman's first line should be line which is at the lowest frequency region at the Lyman series, right? So this is Lyman's first line, because going towards here the frequency increases, right? Then come up with Lyman's second line. So this is the Lyman's second line. I can draw like this at the higher frequency region, right? The second line is always with a greater energy than the first line, greater frequency there. The third line, when drawing the third line, the gaps between the lines should decrease going towards the higher frequency region. Remember that gaps between the lines in a given series should decrease going towards the higher frequency region. That is what we have observed here. Going towards the higher frequency region, the gaps between the spectral lines decreased in a given series, right? So keep it in mind and draw 4 or 5 lines like that, 4th and 5th line. Gaps should decrease going towards higher frequency region, right? So that is the Lyman series. That is your Lyman series. You had just drawn the Lyman series, right? Lyman series of lines. Just draw 5 or 6 lines there, right? Then let's draw the Balmer series. It is very easy. Drawing the Balmer series by seeing the Lyman is very easy, right? How to draw the Balmer series? So it's like this, right? When drawing the Balmer series, what we need to do is just take the second line onwards from the Lyman series. That means this section. Just take this section and copy paste the stuff at the lower frequency region. At the lower frequency region, just copy paste the stuff, right? By taking the second line onward from the Lyman series. Just copy paste this stuff, right? In here, so that you will get the Balmer series, right? So it is like this, the Balmer series of lines, right? These gaps should be maintained as we are copy pasting the stuff, right, from here. So I just maintain in those lines the gaps, right? This is your Balmer series. This is the first line of the Balmer series, which is known as H alpha. This is the second line of the Balmer series, which is known as H beta, H gamma, and this one is H delta, right? Those are the 4 lines of the Balmer series, and those are colored, right? This is red and green, blue and violet. The first 4 lines of Balmer series is actually colored, right? After that, just draw the Paschen series. Very easy to draw. What you need to do is just take the third line onwards. Just take the third line onwards from the Lyman series and just copy paste that stuff at the lower frequency region. Just take the third line onwards here and copy paste the stuff at the lower, further lower frequency region, right? So that is this one portion, right? Copy pasting this stuff, right? Just maintain the gaps, right? So that is it. This is partial series of lines. This is Balmer. This is Lyman. These are the colorful lines, right? So very easy. So keep it in mind, this gap between these two should be higher than the gap between these two. When going towards the higher frequency region, the gap separating the spectral series will increase. Okay. So that is the idea. So that is how we are supposed to draw the hydrogen spectrum, taking this direction as the frequency increasing direction, right? That is the idea. So they may ask the question as this or this, right? So you should be able to answer from any form, right, of the question is asked, right? Okay, that is the idea. So this is the hydrogen spectrum, right? So we had drawn two spectrums, right? So this is what we have drawn last day, right? This is a new stuff, right? So there could be a question like this, labeling the frequency increase region as the right side, right? Okay. Anyway, now let's discuss about the origins of the spectrum. How Niels Bohr described of the origins of this hydrogen spectrum. That is our next discussion, right? Okay. Are you clear up to here, right, Laman? Do you have any questions regarding the hydrogen spectrum and the stuff we have learned up to this stage? Yes. No, not that much, right? You can come up with the chat box even, right? Yes, we have problem, looks like. So yeah, Chris is saying that your volume is very low today, right? Can we increase the volume? Sorry for that, Chris. So we have some issues with the mic today. We'll fix that as soon as possible. Right. Some technical error. So any other questions regarding the lesson, right? We'll try to fix the thing quickly. And now okay. Yeah. Thank you for that comment, right? She's saying that it got very much better just now. That's okay. Right. We'll try to fix that, right? Okay. Is it okay? Right. Right. Then we'll discuss about the origins of the spectrum, right? What Niels Bohr said, Niels Bohr came up with, right, as a reasonings for appearance of these lines, these kind of patterns, right? What are the reasons to appearance of these patterns with the hydrogen spectrum? Let's discuss about that thing, right? So Niels Bohr came up with a revolutionary idea, right? Those ages, right, this idea was actually very new to the atom, right? Basically, he came up with the idea of energy level diagram. He came up with a kind of idea. He said, to appear this kind of a spectrum, to give this kind of a spectrum, the hydrogen atom should be with energy levels. The hydrogen atom should be with energy levels, right? That was Niels Bohr's idea, right? He said, to give this kind of a spectrum, the hydrogen atoms, actually the electrons in the hydrogen atom, right, should be in energy levels. See, like this. So energy levels are like this. This is actually energy level diagram I am going to draw, right? The energy level diagram. Energy level diagram of the hydrogen atom. Right? This is what we are going to draw now. Right? Niels Bohr said, right, to give this kind of spectrum, this kind of patterns with the spectrum, right, the electrons in hydrogen atom should be with energy levels, right? This is the first energy level, he named as N equals 1, the first energy level of the hydrogen atom, right? And this is the final energy level of the hydrogen atom, the infinity energy level. I just draw that thing before drawing the second bar. This is the infinity energy level, right? N equals 1, and this is the infinity, right? 2 energy levels, right? Then between the N equals 1 and N equals infinity, we have the other energy levels, right? So actually in hydrogen atom, to give this kind of a pattern, right, these energy levels are also with a pattern. Energy levels are also appearing with a pattern, right? Because due to that pattern, you get this pattern with the hydrogen spectrum, right? Let's see the pattern of energy levels. But which pattern carries by the energy levels, right, in your hydrogen atom? It is like this, Lamai. If they have asked you to draw the energy level diagram of the hydrogen atom, if they have asked you to draw the energy level diagram of the hydrogen atom, you have to maintain this pattern. This is very important, right? First draw the first energy level. Don't draw the second one then. Before the second one, before drawing the second energy level, just draw the infinite energy level. The first energy level, the infinite energy level. Then, right? Then draw the second energy level. Actually bit higher from the midpoint of the N equals 1 and the N equals infinity. Take the midpoint of the N equals 1 and N equals infinity. This is the midpoint. And the second energy level should be bit higher than that. That pattern should be maintained, right? Without that pattern, you won't get the hydrogen spectrum, right? This is the N equals 2 energy level. It is actually should be drawn bit higher than the midpoint of the N equals 1 and N equals infinity. This is the midpoint of the N equals 1 and N equals infinity. Bit higher than that, you have to draw the second energy level. If you need to come up with the third energy level, you have to maintain the same pattern, right? This is the midpoint. This is the midpoint of this is the midpoint of N equals 2 and N equals infinity. Bit higher than that, you have to draw the N equals 3. This pattern should be maintained. This is the correct way of drawing the energy levels of a hydrogen atom, right? So maintain this one. I'll tell you why. This is very important. Draw the energy levels like this. There are reasons, right? Okay. The fourth one, drawing the fourth energy level. This is the midpoint. Between the N equals 3 and infinity. This is the midpoint. You have to draw the fourth energy level bit higher than that. Right? This is the N equals 4. Like that, you can draw the energy levels, right? This is the infinity one. Right? Drawing the fifth one is still like that. Bit higher than the midpoint of the 4 and infinity. You have to draw the fifth one. I'll draw it like this. Just draw 6 energy levels. That will be enough. Sixth one is also like that, right? It is situated a bit higher than the midpoint of the N equals 5 and the N equals infinity, right? This is N equals 6. Right? This is the energy level diagram proposed by the Niels Bohr for your hydrogen atom, right? So hydrogen atom should be with these kind of energy levels. Without that, right, you can't think of this kind of a spectrum. That is what Niels Bohr said, right? So the electrons in your hydrogen atom should be in, right, should be with this kind of energy levels. That was the idea, right? Okay. Then let's discuss how to come up with, right? So ultimately, you have the energy is right here with the infinity, right? Energy continuum is there. Actually, you can clearly see the energy levels are actually overlapping with each other when going towards the high energy region, right? So you clearly see that thing with this pattern. If you maintain that pattern, you clearly see ultimately the energy levels are overlapping with each other. right? Energy levels are overlapping with each other, right? Okay, so that is the trend. So the point is this. The point is this, right? These are the energy levels of the hydrogen atom. And let's discuss about the origins of the spectrum, right? This is the idea. Niels Bohr said, right? If you take a sample of excited hydrogen atoms, if you take a sample of excited hydrogen atoms means energized hydrogen atoms. Energized hydrogen atoms means hydrogen atoms with some energy. That means the electrons in your hydrogen atoms actually are not in the n equals 1. Basically, when it comes to hydrogen atom, normal hydrogen atom, the electron resides at the n equals 1. No? Electrons occupy the first energy level. With the 288 conformation, you know that no? With the hydrogen, the electron comes at the first energy level. No? Right. But when it comes to excited hydrogen atoms, energized hydrogen atoms, the electron is not here. With those hydrogen atoms, the electrons are at the higher energy levels. You can excite the hydrogen atom by giving some sparks, right? Some electronic sparks, or you can excite by giving some heat to your hydrogen sample, right? By energizing those hydrogen atoms, you can come up with excited hydrogen atoms, right? So with those hydrogen atoms, the electrons may occupy these kind of energy levels, right? Electrons may be here, here, here. So some electrons maybe looks like that, right? More electrons will appear like that. So electrons are at higher energy levels when it comes to an excited hydrogen sample, right? He said, the Niels Bohr said, right? Due to transition of electrons towards n equals 1, due to transition of electrons towards the first energy level, n equals 1, right? Due to the transition of electrons towards first energy level, Niels Bohr said, the Lyman series of lines appears. The Lyman series of lines appears due to the electronic transitions towards the n equals 1 energy level. That was his idea. When the electrons are coming towards n equals 1 energy level from higher energy levels, right? Niels Bohr said the Lyman series appears. How come? Let's discuss a bit about this. How come that is to happen? It is like this, Lama. These are the electronic transitions, right, responsible for appearance of the Lyman series, right? So let's label that and let's have some good idea about this thing, right? So this is all about electronic transitions. Right, responsible for Lyman series. Right, electronic transitions responsible for Lyman series. Let's discuss a bit about that thing. How come this happened? Right, it's like this, Lyman. So Niels Bohr said Lyman. The idea is this. Right? These are the electronic transitions responsible for the appearance of the Lyman series. These spectral lines. Right? Let's discuss the idea. It's like this, Lyman. Right? Let's have some more stuff. Some 5 electronic transitions. Right? Okay. N equals 4, right? The idea is this. So it's like this, Lama. Right? Say you are with 2 energy levels. Say you are with 2 energy levels. The concept is this. Right? See, this is the final energy level, and this is the initial energy level. Right? Think that this energy level carries some, right, 10 joules of energy. This energy level carries some 10 joules of energy. Let's think about that. Consider like that. And this energy level carries some, let's say, 2 joules of energy. The energy of this energy level is 10 joules. Energy of this energy level is 2 joules. Consider like that. So, when you are with the electron at this energy level, when an electron occupies this energy level, when an electron occupies the initial energy level like this, that means that electron is with 10 joules of energy. if an electron is here at the first energy level, initial energy level, that means it is with 10 joules of energy. Right? Always electron should have the corresponding energy to that energy level to reside on that. To occupy the energy level, electron should have the same amount of energy as the energy level. Right? To occupy that energy level, electron should have the same amount of energy as the energy level. Right? That is the idea. So if electron occupy at 10 joules energy level, that means your electron is with 10 joules of energy. That is the idea, right? Okay. So if that electron to come to the 2 joules energy level, if that electron to come to the 2 joules of energy level, 2 joules energy level, that means that electron has to release that 8 joules of energy, to reside on this thing. To occupy the to occupy the 2 joules energy level, electron should have only 2 joules here. When you are to occupy here, you should have only 2 joules of energy. If you are occupying here, you should have 10 joules of energy. Energy related to the energy level should be there to occupy the energy level. So electron to occupy here, starting from here, it has to release its 8 joules of excess energy towards outwards. Right? It has to release the 8 joules of energy to occupy this energy level if you are starting with here. That means actually this energy, the excess energy will be released as a energy photon, right? If an electron transit from a high energy level to low energy level, the excess energy will be released as a energy photon. Photon means it is with a H and a mu. Energy photon means it's a radiation, right, with a frequency. Those are the frequency values appearing at the hydrogen spectrum. Right? When electron transition happens like this, from high energy to low energy level, that electron transition will release the excess energy as an energy photon. That photon is with a frequency. That frequency is marked here. Right? When the electron coming from second energy level to first energy level, that is the lowest energy photon released. When electron coming to n equals 1, that is the lowest energy released as a photon. So it is appearing at here. Its frequency is appearing at here. When it comes to second transition, this is the next lowest energy releasement, right, at the Lyman series when the electron come into n equals 1. So that energy photon's frequency is marked here. Right? You can clearly see the idea. So when an electron coming from n equals 4 to n equals 1, the electron coming from n equals 4 to n equals 1, right? So that you are releasing an energy photon, its frequency is marked here, right? That is the idea. That is how the spectral series of lines appears due to the electronic transitions from high energy levels to low energy levels. When an electron transit from high energy level to a low energy level, the excess energy will be released, right? So that will be released as energy photon, and that photon's frequency is marked as your spectrum, the hydrogen emission spectrum, right? That will give you the clear idea about the hydrogen spectrum, the appearance of spectral lines of your spectrum, right? So that is the idea of the Niels Bohr, right? So he said, when the electrons are coming to n equals 1, starting from the high energy levels, when the electrons are coming towards n equals 1, right? From those released photons, the Lyman series of lines appear. Right? When the electrons are transit into n equals 2, starting from the higher energy levels, when the electrons are coming towards n equals 2, like this, from the n equals 3 to n equals 2, or from n equals 4 to n equals 2. When the electrons are coming towards n equals 2, Niels Bohr said, right, due to those released photons, right, due to those released photons, when the electrons are coming from n equals towards n equals 2, due to those released photons, right, Balmer series of lines appear. Right? That is what Niels Bohr said, right? The Balmer series of lines due to electron transitions towards n equals 2, the Balmer series of lines appears. Electron transitions responsible for Balmer series. Likewise, if the electrons are coming towards n equals 3, starting from the higher energy levels, if the electrons are coming towards n equals 3, those released photons will give you the Paschen series. Electron transitions responsible for Paschen series, right? So that is how the Niels Bohr explained the origins of the spectral lines of your hydrogen spectrum, right? Okay, got the idea? So when the electrons are coming from high energy levels to low energy levels, the excess energy will be released as energy photons, right? So energy photons means those photons are with some frequency. If you are to order those frequency, right, in increasing or decreasing frequency, right, you get the spectral series of lines. When the electrons are coming to n equals 1 with those photons, you get the Lyman series. When the electrons are coming to n equals 2, right, with those photons, you get the Balmer series. When the electrons are coming towards n equals 3, from those released photons, you get the Paschen series, right? If the electrons are coming towards n equals 4, you get the bracket series, and with 5, you get the Pfund series as well. Those are the other two series of lines, right? So that is the major idea given by the Niels Bohr to explain the origins of the spectral lines of hydrogen spectrum, right? That is the idea. So I think you got the idea clearly. You can draw this diagram, Lamai. You can draw this diagram, and afterwards we'll discuss more about this one. So you can start drawing the you may have drawn this one. Just draw this one, right? Just draw this diagram, right? Clearly. And now Niels Bohr had given some name to these n values. Right? These n values are known as quantum numbers. Quantum numbers. These n values are known as quantum numbers, right? Okay. Niels Bohr is the scientist who introduced the quantum numbers concept to the atom, right? Quantum numbers, right? N values are quantum numbers. And we can write the energies as well. Here, we'll write the energies as well. Normal energy is mentioned in kilojoules per mole, right? Kilojoules per mole. So at the infinity level, it is 0. At here, 1, 3, 1, 2, right? So you can put the energies as well. These are energy values. No need to memorize these energy values, Lamai. No need to memorize these energy values. These are energy values related to the energy levels, right? Just quickly draw this one, Lamai. Just quickly draw this one. So I'll give you 2 minutes. You can have a screen fetch as well. Oh, else I'll send you a picture, no? That is better? Yeah, I think it's better, no? So I'll send you a picture to your WhatsApp. right? Then you can complete the diagram, right? And then we can go for further explanations, right? So let's take a picture here, right? Take a picture here. I'll send you a picture, Raman, of this one, right? So you can properly draw that thing now. So when drawing this one, right, make sure first draw the n equals 1, then draw the n equals infinity. So when drawing the n equals 2, it should be a bit higher than the midpoint of the n equals 1 and infinity. When drawing the n equals 3, it should be a bit higher than the midpoint of the n equals 2 and n equals infinity. Like that, you can continue drawing the n equals 4, 5 and 6. Right, when drawing the intervals, just use that technique. Right, that will be very important. I'll explain why. Right, I'll explain why. We'll send you the picture of this one. Right now. Right. Okay. This is right now. We'll send you the picture, right? Okay. So you may have received that thing. Right. Then this is the engineer diagram of the hydrogen atom. So Laman, in your question paper, if they have asked you to draw the hydrogen spectrum, just draw only this one. Just draw only this one, right? Just draw only this one. If they have asked you to draw the hydrogen spectrum, only this is required, right? If they have asked you to draw the energy level diagram of the hydrogen atom, right? Energy level diagram of the hydrogen atom, then you need to draw this diagram, right? Don't draw this one, right? That is the idea. You have to answer for what they are asking, right? Okay. If the energy level diagram is asked, just draw this one, right? Okay. Right. Let's describe the patterns with the use of this diagram. Let's describe the patterns appearing here with the use of this diagram. Okay, it's like this. First thing. The first thing here is I'll explain you why you need to draw the n equals 2 energy level. Why you need to draw the n equals 2? Why do you need to draw the n equals 2 bit higher than the midpoint of the n equals 1 and the infinity? I'll explain that. First, I'll explain that. Why you need to draw the n equals 2 bit higher than the midpoint of the n equals 1 and infinity. The reason is this. Samay. So, take these two lines. This line, take this line and this line. Take these two lines. Consider these two lines. This one, I put it as A, and this line B. Right? Take these two transitions. Right? So basically, another thing you should know is actually, right? You can come up with the energy of the energy photon. By considering the energy gap between the two energy levels, right? by considering the energy gap between two energy levels, right? You can come up with the energy of the each photon, right? So it is 10 joules, this 2 joules. The energy gap between the two energy levels is 8 joules. That will be the energy of the photon. So energy of the photon can be calculated with the use of the energy gap between the two energy levels of electronic transition, right? Keep it in mind, right? From one side, it is important, no, right? Okay. Then consider these two electronic transitions. Laman, this transition, this A electronic transition is actually belongs to Lyman series. This A electronic transition is actually belongs to Lyman series. This is the lowest energy line of the Lyman series. This is the lowest energy transition of the Lyman series. This is where you get the lowest energy photon with the Lyman series. So this is corresponds to this. This corresponds to this. That transition corresponds to this line. The lowest energy line of the Lyman series. Frequency low means energy low. Lowest frequency line of the Lyman series means lowest energy line of the Lyman series. Take this B. What is this B? B is actually when an electron transits from the n equals infinity towards n equals 2. This is the electron transition coming from n equals infinity to the n equals 2. This means this is the highest energy line. This is the highest energy line. This is the highest energy line of the Balmer series. This is the highest energy line of the Balmer series. Coming from n equals infinity towards n equals 2 means that is the highest energy gap. That is the highest energy gap available with the Balmer transitions. With the Balmer transition, that is, this is the highest energy gap available. So this is the highest energy, highest frequency. This is responsible for the highest frequency line of the Balmer series. Highest frequency line of the Balmer series. So if you take the Balmer series, other lines, ultimate lines get overlapped like this. For any series, ultimate lines get overlapped, right? Because gaps between lines becomes closer, and ultimately those will overlap, right? So that B line responds to this. That B transition is actually due to this. Actually, this line is due to the B transition, right? What you clearly see here is actually all the lines of the Lyman series. All the lines of the Lyman series are with greater frequency. That means greater energy than all the lines of the Balmer series. With this diagram, what you clearly see is all the lines of the Lyman series are with greater energy. Greater frequency means greater energy than all the lines of the Balmer series. That means even the lowest energy line, even the lowest energy transition of the Lyman series is with a greater energy than the highest energy line of the Balmer series. Again, I am telling you, even the lowest energy line, lowest frequency line with lowest energy line of the Lyman series is with a greater energy. Even the lowest energy line of the Lyman series is with a greater energy than the highest energy line of the Balmer series. Highest energy line of the Balmer series. Highest energy line of the Balmer series appears when an electron coming from n equals infinity coming towards n equals 2. When an electron from n equals infinity coming towards n equals 2, this highest energy transition of Balmer series appears. The lowest energy transition of Lyman series appears when electron coming from 2 to 1. So you clearly see even this thing is with a greater energy than this. That means this energy gap should be with a greater energy than this energy gap. This energy gap should be with a greater energy than this energy gap. That is why I say, right, that this gap should be greater than this gap. The gap between n equals 2 and n equals 1 should be greater than the gap between the n equals infinity and n equals 2. That is why I say, right, that when drawing the n equals 2, it should be drawn bit higher than the midpoint of the 1 and the infinity. N equals 2 should be drawn bit higher than the midpoint of 1 and infinity. Then only you get this gap as a greater gap than this gap, the gap between the infinity and the 2, right? I think you clearly understood the concept. That is why I said that when drawing this diagram, you have to maintain that pattern. When drawing the n equals 2, it should be drawn bit higher than the midpoint of the 1 and the infinity. When drawing the n equals 3, it should be drawn higher than the midpoint of the 2 and the infinity. Like that, these integers should continue, right? Then only you get this kind of a nice diagram as the integral diagram of Haydn atom, right? Got the idea? Right. That same logic can be taken for this line and the final line of the partial series as well, right? To confirm that then this gap is greater than this gap. This gap is greater than this gap. To confirm that, you have to take the final line of the partial series and the first line of the bound series. The same logic, right? So that is clear. That is the first thing you should know. That's the first thing you should know, right? Okay, second one. We'll write these things down. We'll write these things with the next page, right? But first we'll discuss the stuff. Afterwards, you can write. Okay, right. The second thing, that copy pasting stuff, right? Why we are able to copy paste the things like we have done, right? So actually, when drawing the Balmer series, what we have done is just take the second line onwards from the Lyman and just copy paste in the stuff as the Balmer series. Just take in the third line onwards and copy paste in the stuff as the partial series. That is what we have done, right? So let's consider what is the reason for that, why we are able to do so, right? With this, let's discuss those things with the use of this engineering diagram, why we are able to do so, the copy pasting stuff, right? Okay, see, it is like this. Let's consider this engineering diagram again, right? And discuss about that pattern, right? So this was the first line, right? That is all about Lama. That is all about gaps. That is all about gaps between the spectral lines. That's all about gaps between spectral lines, right? Copy pasting stuff means actually gap between the 2 and 3 is same as the gap between the 1 and 2. Gap between 2 and 3 is same as the gap between 1 and 2. That was the idea, right? Gap between the 3 and 4 is same as the gap between the 2 and 3 of the Balmer. Copy pasting is that. Gap between the 4 and 5 is same as the gap between the 3 and 4 of the Balmer. That is what happens when you have copy pasting stuff. Let's discuss why is that. How that is possible with the use of this engineering diagram. Let's discuss about that. It is like this, Laman. The gaps between spectral lines, right? The gaps between spectral lines is due to this, no? So it is like this, no? Let's consider that. If right, I'll take the numbers as well. This transition, when an electron coming from here to here, when 1 mole of electrons coming from here to here, it is all about 1 moles, right? So last day we had discussed about that thing. It is all about 1 moles, right? So when 1 mole of electrons, coming from here to here, the amount of energy released will be given by the gap between the two energy levels. Will be given by the gap between two energy levels. So this concept, right? When an electron is transiting from high energy to low energy level, the gap between the two energy levels will give you the energy of the photons, right? Okay. So when 1 mole of electrons to transit from here to here, the released energy as photons will be given by the gap between these two, 1312 and the 328. That gap will be given as, I'll calculate that thing as 984. I just calculated the value, right? 984. That was the gap between these two. So this amount of energy will be released when 1 mole of photons coming from here transit to here, right? Let's consider. When 1 mole of electrons transit from here to here, right? The released energy will be given by the gap between 3 and 1. Right? Gap between the 3 and 1 will give you the amount of energy released as photons when 1 mole of electrons transfer from here to here. that will be, I will take the gap between this one and this one, right? That will be like, I just calculated, right? 1000, that value is actually 1166, right? So this gap is 1166, this gap between these two, right? So this 984 correspond to this, the frequency. If you take let's take this as energy, both are same, energy or the frequency both are same. Just multiplying with a constant, you get the energy. So you can convert the frequency to energy by just multiplying with a constant, right? So let's take the energy values. It is better to easy to explain then, right? That energy value is actually coming from 984. That second energy value coming from 1066. If you take the third energy value, that comes from, when it will transfer from 4 to 1, that is actually, if you take that gap, it will be 1230. I just take the gaps, right? Right. So if you take the same things appearing with these ones, taking the gaps, it will give you like 182 and kind of 246. This difference actually, this difference is equal to, if you take these values, this difference will be equal to this difference. If you take the values, you will see, right? What is that difference actually? What is that difference? That difference is actually, that difference is this much. This is the difference. This is the difference. Energy difference between the first and second line. Energy difference between the first and second line of the Balmer. This is the first line's energy. This is the second line's energy difference. Energy difference between the first and second lines is this much. That is actually the energy difference between the second and third lines of the Lyman. Second and third lines of the Lyman. Energy difference between the first and second line of the Balmer is actually the energy difference between the second and third line of the Lyman. That is the idea. So you can even count that thing. Right? Let's come up with another one. Energy difference between the second and third lines is this much. This energy difference between second and third lines, that will be same as the energy difference between the third and fourth lines. 1, 2, 3, 4. Third and fourth lines of the Lyman. So energy difference between the second and third lines of the Balmer is same as the energy difference between the third and fourth lines of the Lyman. Got the idea? No? That is why we are saying that you can copy paste the stuff like that, like we have done, right? So if you take another one, the energy difference between the third and fourth lines, this difference between the third and fourth lines of the Balmer is actually the energy difference between the fourth and fifth lines of the Lyman. See? The same difference, right? That is why we say this difference is same as this. That is same as for the Paschen as well. See? This energy difference. See? The same thing. Energy difference between the first and second lines of the Paschen is same as the energy difference between the third and fourth lines of the Lyman. Same as the second and third lines of the Balmer. Same thing, right? You can clearly see. So that is why we are saying that you can draw the Balmer series by just copy pasting the second line onwards at the lower frequency region. you can clearly come up with the partial series by just copy pasting the third line onwards, right, at the lower frequency region. That is possible because of this pattern. The energy difference are equal for those, right? No, that is the idea, right? So that is why we say that copy pasting stuff can be done, right? The other thing, next one we need to consider. The next thing we need to consider is actually the reason for these lines to get closer to each other when going towards higher frequency region. The reason for these lines to get closer to each other when going towards higher energy region. The reason is clear with this one. The reason is clear with this one. The reason is clear. The reason is actually, right, you clearly see, right, the energy gaps here, the energy differences means the energy gaps here, those will decrease going towards higher energies. Going towards higher energies, you clearly see the gap between the 1 and 2 is this much. Gap between the 2 and 3 is this much. Gap between the 4 and 5 is this much. You clearly see the gaps will decrease going towards high energies. That is why the gaps between the lines also get decreased. Right now, that is the idea. So the gaps between the spectral lines decrease because the energy levels become closer to each other when going towards high energy regions. Right? This gap is due to Lamai. This gap is due to this gap. No. This is the energy 984 that represents this. This is the energy 1166 that represents this. The gap, energy gap, is due to this gap. No. Like that. This energy gap is due to this gap. No. Right? So this gap is smaller than this gap. No. So you will clearly see the gaps between the spectral lines should decrease as the energy levels become closer going towards higher energy region. Right? That is the third idea. So you should know the reasons, right? You should know the reasons to appear the spectral lines in the hidden spectrum like this, right? So those are the reasons. Okay. So one by one, let's complete the note. So you can complete this one, right? We had sent you the picture there. So by looking at the picture, you can complete this one. Then next at the next page, we are to write the note. What we have discussed, just let's write the stuff, right? Okay. At the page number 18, right? Let's go to the stuff and we'll write, right? Okay. Yes, right. It is said like this, right? Some important facts on hydrogen spectrum. First of all, do you have any questions? First of all, do you have any questions regarding the stuff what we have discussed up to now? Do you have any questions? If so, I'll answer those and then continue. So, any questions regarding the stuff? Sorry? Sorry. Sorry, I don't hear you. Just tell me again. Sorry.
In O level, hydrogen atom we get in the first one energy level, two atoms. Sorry, one atom, two, one atom, no, one atom. So two, no, two. Only one energy level only two, no, O level. But here, energy level goes to infinity, no, for hydrogen.
Yeah. Okay. Yeah. The question, yes, I'll tell you. Yes. Yeah. Good question. So your friend's question was actually when drawing the hydrogen atom in O levels, right? When drawing the hydrogen atom, you just draw the hydrogen atom like this, no? This is just the hydrogen atom in your O levels. Only one electron is there, like that, no? You just draw the hydrogen. Right. So then Chris is asking, now we have more energy levels now. Yeah, why is that? Yes. Yeah, good God. Anyone with a good explanation? Yes. Right. Shashadara is there. So yes, any good explanation for the question asked by your friend? Yeah, got the answer. Yeah, that's the case, right? So that is the case. I think Chris, you got the answer. It's like this, Lama. In hydrogen spectrum, we are not considering the normal hydrogen atom. This is the ground state hydrogen atom. This is the ground state hydrogen atom. Ground state hydrogen atom. Ground state hydrogen atom means the lowest energy hydrogen atom. The hydrogen atom with the lowest energy. There, your first, there your electron resides at the n equals 1. There your energy resides at the occupies the n equals 1. But here we are dealing with some excited hydrogen atoms. Some excited hydrogen atoms. Excited hydrogen atoms means, right? I'll draw. Let's I draw those things here. Excited hydrogen atoms means when you have supply some energy. When you have supply some energy to this one. So even this one you have with some energy levels, right? But we haven't mentioned that thing because no use, because only the electron is appearing here. But when it comes to excited hydrogen atoms, right? That electron is right actually went to this one like that. So according to the energy they have absorbed, you can supply energy via thermal energy, via electronic sparks, right? Kind of those things you can supply energy. When electrons gain those energy and get excited, those electrons can go to n equals 2, n equals 3, n equals 4, n equals 5 like that, right? So so that in a population of hydrogen atoms, right? You see some electrons are appearing at the n equals 1, n equals 2 excited hydrogen atoms. So n equals 1, n equals 2, n equals 3, right? Some electrons are appearing at the n equals 2 for excited hydrogen atoms. Excited hydrogen atoms. Some electrons are appearing at the n equals 3, third energy level. Some electrons are appearing at the n equals 4. That thing will happen with the excited hydrogen population. Excited hydrogen population. That is why we need to consider all these energy levels of the hydrogen atom. But when it comes to alone one ground state hydrogen atom, the electron is at the n equals 1, so no need to consider any other energy levels. But when it comes to excited hydrogen population, more hydrogen atoms, some excited more hydrogen atoms, right? Then with some hydrogen atoms, the electrons are appearing at n equals 2, for some n equals 3, and for some n equals 4. So that we have to consider all the energy levels there where electron can be occupied. Some possibilities there for electron to occupy, right? That is the reason. Yeah.
But that one and only electron, when you supply the energy, it jumps to different energy levels or the multiple electrons?
Yes. Another good question. Yeah, you should ask that thing. Any answer? I'll like to forward that question to your friends. Anyone of you have a good answer for that thing? He's saying this thing. He's saying in hydrogen atom only one electron is there. In hydrogen atom only one electron is there. Your friend is saying that. But here you are coming up with more electrons, more electronic transitions. So how can it be possible with one hydrogen atom? That is the question. So anyone with a good answer? Again, I'm telling you the question. These are good questions, right? Your friend Chris is saying that in hydrogen atom only one electron is there. So even for excited hydrogen atom, only one electron should be there. So only one electron is there. No? If it is to excite, just one electron is there. Should be only one electron. So one electron in a high energy level. Okay. Then how come it is possible to have this amount of transitions with such a hydrogen atom? That is what he is asking. Right? Any good answer from your friends? Yes. Sorry. Deshan, right? Sorry, I didn't hear you properly. No, I'll tell you the reason. This is not the possibility. It's like this. Lama, it's a very good question. You should ask that. Huh? The thing is this. The hydrogen spectrum is observed not by a single hydrogen atom. Remember that. That is very important to note that. the hydrogen spectrum is observed not from a single hydrogen atom. Actually, you can't isolate a single hydrogen atom. How can? How could it be possible to isolate one single hydrogen atom? So, I'll tell you the practical reasons, right? So, you can't isolate one single hydrogen atom, Lavan. If you are to isolate one single hydrogen atom, right, you need to take what kind of a mass? What kind of a mass of hydrogen do you need to take to isolate one single hydrogen atom? So, you need to take this kind of a mass, right? I'll come up with that. You need to take Lamai to isolate one hydrogen atom, to take one hydrogen atom, you need to come up with what should be the weight to come up with a hydrogen sample. That sample's weight mass should be, for 1 mole of hydrogen atoms, it is 1 gram. It is 1 gram per 1 mole of hydrogen atoms. Per one hydrogen atom, it is divided by the Avogadro's. So this is the mass of a one hydrogen atom, right? So it is kind of a, I'll just take take some number, it will be some value, right? 1 point some value into 10 to the power minus 24. This is the amount of grams you need to come up with to take one hydrogen atom. 10 to the minus 24 grams. Can you isolate this thing? Do you have any kind of a scale to measure this kind of a value? So remember that you can't isolate one hydrogen atom. So hydrogen spectrum is not observed by a single hydrogen atom. It is observed by a population of hydrogen atoms. It is observed by numbers of hydrogen atoms. I earlier also discussed about that thing, the population of hydrogen atoms, right? So it is observed by numbers of hydrogen atoms. If you have to take 1 gram of hydrogen sample, how many hydrogen atoms are there? There are 6.022 into 10 to the power 22 atoms in 1 gram of hydrogen sample. In 1 gram of hydrogen sample, if you are to take 1 gram of hydrogen sample, right, you have this amount of atoms, Avogadro's number of atoms. So they have observed the hydrogen spectrum via such a sample, not from one single hydrogen atom. So we have this amount of hydrogen atoms, so that few amounts of hydrogen atoms will excite to n equals 2. With some hydrogen atoms, the electron will excite to n equals 3. With some other hydrogen atoms, their electrons will excite to n equals 4. Like that, the population will be there. So that is how you observe the hydrogen spectrum, not from a single hydrogen atom. Especially mention that. Right? Okay. Any other questions? I think Chris, you got the answer. Do you have the question? Okay, right. Okay. Right. That is the idea. So any other questions, Lava? So just ask the questions, because these questions are very important, right? To know the concepts clearly. If you guys are within. Sorry, again, sorry, tell me again. I just don't hear it. You? Can't we draw the sorry, can you send me the thing? I not clear here. Can't you send? Can't we draw the? Deshana, question. If you can just send me a message to the chat box, then it will be clear. Something. We are having a bit of problems today with the mics and the sounds, right? So okay, you can send the if you can just send the message, right? Or else just send it to the my number. I'll check. Yes, I hear you. Again, tell me, right?
Sir, I asked whether we can or not draw the shortest line first when drawing energy level diagram.
Shortest. Ah, yeah. Again, I got the I got the point, right? Okay, your friend is asking when we draw in this one. Basically, we first drawn the greatest energy transition. I think she is asking, can't we draw this one like this? I think that is what she is asking. Good done. The question should be asked, right? So, I think this is what she is asking. She's asking, can't we draw this one first? Is this the question, Naru?
Yes, sir.
Ah, yeah. Yeah, what is the comment from your friends? Yeah, tell me. What you say? Chris. Shishadara, you have some ideas. You may have some ideas. Is this true? Is it true for the transitions for the Lyman series? Is this okay? To draw the transitions like this? You can come up with the chat box as well. All right. Shishadara, you have a question asked with the chat box. I think you got the answer for the that question. If you still have a problem, just ask again. Right? Yes, this is true. No worries. No worries, right? I'll tell you why, right? So I may say you can draw even like this. If you need, right? Just draw it from here. Oh, no worries. First line. Oh, second line from here. Oh, no worries. The third line now. I'll put it here. Any question? No worries. Anyway, if the electron is coming towards n equals 1, that is definitely transitions of Lyman series. If the electron is coming towards n equals 1, those are definitely transitions of Lyman series. No worries. Right? If that is coming from the nearest available higher energy level, it is coming from nearest available higher energy level, that is the first line. That is giving you the first line of Lyman series. It is coming from the next highest available, and it will give you the second line of Lyman series, then the third line of Lyman series. No worries. You don't need to come up with the pattern and the stuff like that. No need. If any transition is happening, electron is coming towards n equals 1, that is Lyman's. Just for easiness of understanding, they went with this kind of a diagram, right? Some proper nature, right? No need, right? No need to write. No need to think of that. This line is at this one is at the right hand side, so I need to write the red line at the right hand side. There's no such idea. There's no such idea. But what happens if you are to consider the other spectral line series, right? So when it comes to if the frequency is increasing towards this direction, then the red line appears at here, no? The red line will appear at here, no? Right? Then the blue line will appear at here, no? Sorry, the green line. Sorry, the green line will appear there, right? Then the blue line will appear, right, with some higher frequency here, and the other line, delta line, will appear here. Still, for this kind of diagram, still this is okay. Still this is right. Right? No worries. No need of drawing the transitions directly given as the spectrum. These are two different things, right? I think you got the answer. Is it clear? Then?
Yes, sir.
Right. No? Okay. Any other questions? Right. No? Okay. Clear, no? Shashadra, I think it's okay, no? Your question is right, no? Hi. Right, let's come up with the stuff then. I think you have clarified the problems with you, right? Right, let's write the note. Leave, just write this one, right? Okay. And if you have any other questions, just put in the chat box, right? Okay. Right. Let's write the stuff, right? Some important points, right? It says like this. Some important facts on hydrogen emission spectrum. Right? Some important facts on hydrogen emission spectrum. Right. First point, it says H atomic spectrum is a result of electron transition to lower energy levels of excited energized hydrogen atoms. That is correct, right? Then put a point and write this thing, Lamai. At that space, just write under the first point. Just write this thing. In hydrogen atom, there should be write it in red color, energy levels come to the normal color, Lamai, and they are named as N equals 1, N equals 2, N equals 3. They are named as N equals 1, N equals 2, N equals 3, some dotted lines, etc. 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 Right? To the same point, just write. These n values are introduced by. These n values are introduced by. This is all about these things, right? These n values are introduced by. 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 Write it in red color. Niels Bohr. These n values are introduced by Niels Bohr. Come to the normal color. And they are called as write it in red color. Principal quantum numbers. Right? Principal quantum numbers. Right? It's principal quantum numbers. They are called as principal quantum numbers. Right now. First introduced as quantum numbers, Lamai. With time, they have introduced few more quantum numbers, right? Then this quantum number set was referred to as principal quantum numbers. That was the ancient idea, right? Okay. Right. Principal quantum numbers. Right. Just come to the second point. Next point. Under the first point, the next line. Next point. Under the first point, next point, right? With the normal color, just write. When an electron falls from an initial energy level, when an electron falls from an initial energy level, within brackets Ni, initial energy level, Ni. The energy levels are named as N values, no? Ni, energy level, initial, Ni, to a final energy level, within brackets Nf, to final energy level, within brackets Nf, to final energy level Nf. A photon is released. We have discussed this idea, right? It's like this, no? Right? Don't just draw the one, right? Just see what the stuff, right? So when an electron coming from initial energy level to final energy level, right? What they are saying is a photon of energy will be released. Photon of energy will be released. That is the idea, right? A photon of energy will be released. Right? Okay. Just write this up, right? The energy of that photon, we can draw this thing afterwards, right? First write the para and then we can draw, right? The energy of that photon, 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 just write E photon, E subscript photon within brackets, E photon, the energy of that photon within brackets, E photon, close brackets, is equal to the energy gap is equal to the energy gap is equal to the energy gap is equal to energy gap. You can write delta E, energy gap delta E, energy gap delta E, energy gap delta E, within brackets you can write delta E, energy gap within brackets delta E, close the brackets, between corresponding energy levels, between corresponding energy levels, energy gap between corresponding energy levels, right? Then Lama, you can draw this one, right? You can draw this picture, n equals 1 to n equals f, right? You can use all the space available there, the rest of the space available there, n equals, when you coming from n equals to 1 to n equals initial to final, some photon will be released. That photon's energy will be given by the, right, two energies of the energy levels. So if it is the EI and the EF here, that energy will be given by, right, actually E photon will be given by the energy gap, right? Energy gap will be given by actually EI minus EF. That is the idea, right? So one can write the H mu is equal to EI minus EF or HCO lambda. Energy of photon can be given in these two methods, no? EI minus EF. Right, no? Okay. So energy of photon is given by H mu or HCO lambda. If the frequency is given, it can be taken as H mu. If the lambda is given with the wave, it can be taken as HCO lambda. That is equal to the energy gap. Right? Just draw this stuff, this whole stuff. Right, hard. Let's continue. Right, next one. Next point. It says the first four. Lama, you can take a screen capture as well, right? If you are not with enough time, just take a screen capture. Right? Okay, let's continue. The first four lines observed in hydrogen spectrum belongs to wavelengths of 656, 486, 366, 410. No need to memorize the numbers, right? No need to memorize the numbers. Those won't be asked, right? No need to memorize the numbers. But you need to memorize the colors. You need to memorize the colors, right? No need of numbers, but the colors should be memorized, right? And these spectral lines are due to electron transition towards n equals 2, right? The Balmer series, right? This series of lines is called the Balmer series, and those wavelengths belongs to visible region of the electromagnetic spectrum. That is why you see the colors, right? As the radiations are appearing at the visible range, that is why you see the colors. And note that even at the last day I have mentioned that, note that only the first four lines Only the first 4 lines belongs to the visible region, right? Only the first 4 lines of the Balmer series belongs to the visible region. Definitely note that thing. It's very important. Not all the lines of the Balmer series belongs to the visible region. Not all the lines of the Balmer belongs to the visible region. Only the first 4 lines. Only the first 4 lines of the Balmer belongs to the visible region. Beyond the violet colored line, beyond the purple color line, the other lines belongs to UV region, right? Lines with greater energy than the purple, lines with greater energy than the purple are known as ultraviolet, violet, ultraviolet. So only the first 4 lines of the Balmer series belongs to visible region. The next lines, rest of the lines of the Balmer series belongs to UV region. Remember that. If such a statement was there like all the lines of the Balmer series belongs to visible region, that statement is false. If a statement was there like all lines of the Balmer series belongs to visible region, statement is false. Only the first 4 lines of the Balmer series belongs to the visible region. Beyond that, lines with greater energy than the violet belongs to ultraviolet region, UV region. Remember that. It's very important. Huh? In resource book as well, they have mentioned this one as partially visible, not as visible. This is IR, this is UV, but this is partially visible. That means only the first 4 lines are belongs to visible. The other lines belongs to UV region. Remember that. Very clearly, you should know that, right? Okay. Let's complete the stuff for that space as well. So let's draw the points there. This is all about the Balmer series, right? Just copy this table, right? Name of line, color, and the electronic transition. Right? So the name of line H alpha, first line, H beta is the second line of the Balmer series, H gamma is the third line, H delta is the fourth line of the Balmer series, right? So fourth line first line means always the lowest energy line of series, right? Second line is next lowest energy line, like that. The colors, this is red. Just color this stuff, Lamai. Then it will come to your mind, which is memory, right? Red, green, blue, violet. Those are the colors. Just color the things. Right? Electronic transitions. It is very easy to take the electronic transitions of these lines. So Balmer series means always the electrons are coming towards n equals 2. Balmer series means the electrons should coming towards n equals 2. That is what Balmer series means. The colored lines appear as the Balmer series. So from where to start up with? So basically first line means the electrons are coming from the nearest higher energy level. The first line is that coming from the nearest higher energy level. Nearest higher energy level is n equals 3. To the n equals 2, the nearest higher energy level is n equals 3. That is the first line of the Balmer. The second line means from the next nearest higher energy level. From the next nearest higher energy level, n equals 4. Then n equals 5 and this is n equals 6. That is how to come up with the electronic transitions response to the colored lines of the Balmer series. Right? Just do this one, Lamai. Quickly come up with this table. Quickly draw this table. So these are Balmer lines. That means definitely electrons should stop at the n equals 2. Balmer lines, n equals 2, towards n equals 2. So the first line means coming from the nearest higher energy level, n equals 3. The second line coming from the electron transition coming from the next nearest higher energy level, n equals 4, 5, 6, like that. You can continue. Quickly draw the stuff, Lamai. So I'll send you a picture as well for this one, right? If you don't have enough time to write the stuff, right? So you can complete the note now. We'll try to discuss more stuff, right? So I'll send you the send you a photo of this one, right? So you can complete the note, right? Right. Let's come to the next point, right? Next point. That is at the page number 19, I think, no? Yeah, next point, right? It says like this. So we'll send you the photo of this one, right? For your stuff, just see. So you can complete the note after the class, right? Got the idea? If you have any questions now, just raise your hands and ask the question, right? No worries, right? When we are discussing, just if you have any questions, just put that to the chat box, or you can raise your hands. We'll give you the answers there, right? Okay. Let's continue there, right? Next one. At the next page, it says, with time, few other spectral line series also identified. With time, few other spectral line series were identified. Okay, that is what they are saying, right? So actually, the first series to identify, first series of lines to identify in the hydrogen spectrum is actually the Balmer series, lamai. Those are the colored lines, no? The colored lines are the ones first identified by the scientists, right? In ancient times, the first series to identify in your hydrogen spectrum is the Balmer series. Then after that, when they are scanning, right, towards the lower frequency regions and the higher frequency regions, after identifying the Balmer series of lines, when they are scanning towards the lower frequency regions and higher frequencies, right, then only they came to know about the Lyman, Paschen, Brackett, and the Fund series, right, series of lines. So first series to identify was Balmer. Then only by scanning they found the other series appearing, right? So let's come up with those as well, right? With time, few other spectral series also identified. That is also mentioned, right? Let's come up with another table of content, right? Some summarized ideas that we have discussed so far, right? So we can have this table as well. Name of series, right? Due to electronic transitions, towards, right, then region of electromagnetic spectrum, right? This is the idea. So name of series Lyman, Balmer, Paschen, Brackett, Fund. Lamai, more series are available, right? But in our A levels, we need to know only about these 5 series of lines. But if you can search on the internet as well, right? Few more series are available. N equals 6, N equals 7, N equals 8. Those series are also there. But knowing up to Fund is enough for our A level stuff, right? Due to transitions towards N equals 1, the Lyman. Due to transitions towards N equals 2, the Balmer. Due to electronic transitions towards N equals 3, from release photons, the Paschen series is arrives, right? This towards N equals 4 and this is towards N equals 5. The region of electronic spectrum, the Lyman comes with the UV region, ultraviolet, and the Balmer comes with the visible region. We can say visible and some UV as well. The Paschen comes with Paschen, Brackett, and Fund. All the things comes with IR region, ultra or the infrared region. Right? So you can complete this one as well. So you can use hold the space to complete this diagram. This table, right? You can use the hold the space available there. with time few other spectral series are also in fact that space you can come up with this thing. Quickly write the stuff now. Right? Now today we are continuing the class till 11, right? So okay, we'll continue till 11 for today's onwards, right? So last day I have told you, right? Because we need to catch up the other guys, right? So we have actually started right recently. So right, we have to run through. Right, so yes, we'll do the class till 11, right? This right now. Okay, let's continue. Right, I'll send you the pictures. Right. Right. Let's continue the stuff, right? Next point, it says, when considering series of lines of any individual series, when considering series of lines of any individual series, right? Comma is there. What will happen? Line. When considering series of lines, in individual series, what will happen? When going towards higher energy region or when going towards higher frequency region, the gaps between central lines decrease. Gaps between central lines decrease. Right? When going towards higher energy or the higher frequency region, the gaps between central lines decrease. Let's write that stuff, right? When considering a series of lines of any individual series, with the red color, just write. Gap between spectral lines decreases with the increasing frequency. Gaps between central lines decreases with the increasing frequency. Gaps between central lines decreases with the increasing frequency. Right? Increasing frequency. Right now? With the increasing frequency. Gaps between central lines decreases with the increasing frequency. Right. Within brackets you can write energy. Increasing frequency means increasing energy. Both are same, right? E is proportional to mu nu. Increasing frequency means increasing energy, right? Okay. At the next line, just write. Come to the normal color. And write at the next line. This must be due to. Yes, the reason we had discussed. This must be due to the gap between the energy levels, no? Also decreases going towards higher energies, no? In the hydrogen energy level diagram. In the hydrogen's energy levels, right? Gaps between the energy levels also decreases going towards higher energy. Just write that thing, right? This must be due to, right? Write it in red color. Energies of energy levels becoming more closer. Energies of energy levels, you see? Energies of energy levels becoming more closer. Energies of energy levels becoming more closer. When going from n equals 1 to n equals infinity. Energies of energy levels becoming more closer when going from n equals 1 to n equals infinity. Right, no? So that is the idea. Right. Okay, that is clear, no? You should always know the reasons as well, right? Because we have such kind of a question type, right, in MCQs. You may have come across those things, you may have seen that those things with your workbook, right? Just go to the workbook questions with the hidden spectrum. You will see at the end there are 10 more questions, right? As first statement, second statement questions. They are to clearly answer those things properly. You should know the reasons, right? You should know the reasons as well, right? So that you should know the reason, right? Why these gaps between central lines decreases going towards higher frequencies, right? Because the gaps between the energy levels also decreases going towards higher energies, or energy levels becoming closer when going towards high energy region, right? That is the idea. That is the reason, right? Okay. Next point. Next point, it says the gaps separating each series will decrease going from Lyman to Pfund. See, that is very important, right? Even though gaps between spectral lines of a given series, gaps between spectral lines of a given series decreases going towards higher frequency region, gaps separating spectral series like this, gaps separating spectral series will decrease going towards lower frequency region. Gaps between spectral lines of a given series decreases going towards higher frequency region, but gaps separating spectral series decrease going towards lower frequency region. So ultimately, your Paschen and Brackett series of lines get overlapped with each other. Brackett and Pfund series will overlap. So their gap is very minimal. So gaps separating the spectral line series decreases going towards lower frequency region. Gap separating series of lines of one series, given series, decreases going towards higher frequency region. Take that thing, right? Okay, that is what it says. Gaps separating each series will decrease going from Lyman to Pfund. Ultimately, Brackett and Pfund series overlap in IR region. Got the idea, right? Okay. Next one. Next one is very important now. Next point is very important. Next point is very, very important, right? Very, very important, right? I'll erase this thing. Next point is about the ionization energy of the hydrogen atom. Next point is about the ionization energy of the hydrogen atom. Ionization energy of the hydrogen atom. The ionization energy of the hydrogen atom. Let's discuss about that thing. The ionization energy of the hydrogen atom. Lavan. What is the ionization energy? Right? What is the ionization energy? Right? I'll just draw the Lyman's lines as well. Right. What is meant by ionization in Laman? Yes, in small ages you may have learnt about the ionization energy. What is ionization energy? Ionization energy is the minimum energy needed to eject an electron from a gaseous atom. From a gaseous atom to release an electron, the minimum energy needed, that is referred to as the ionization energy. So the point is this. So basically when it comes to hydrogen atom, the electron is at the n equals 1. No? Electron is at the lowest energy level for the normal hydrogen atom, normal ground state hydrogen atom. For ground state hydrogen gaseous atom, the electron is at the n equals 1 energy level. The 288 configuration, with that thing also you write the electron at the first energy level for the hydrogen atom. Right? So the ionization energy means, right, you are trying to transfer this electron to where? To the n equals infinity. if you are to transfer this electron to n equals infinity, this electron will release from the atom. The electron will release from the atom, right? If you are, it's like this, right? You will supply some energy. You will supply some energy. Let's say you will supply some energy photon, which will carry the energy needed to eject the electron from the atom. Right? If the energy of that photon is transferred to this electron, it can get excited. And if it is to come towards the n equals infinity, this is the ionization. The minimum energy needed to eject an electron. If you can supply more energy than that, the electron will be here. That will be ejected. So the minimum energy needed is this. This is the final last energy level available with the hydrogen atom. So when it comes to here, it is almost ejected. If a bit of energy is there, it is almost gone. So this is the minimum energy needed to eject the electron from the hydrogen atom. If you had supplied more energy, it will be further gone. Minimum energy is this one. If you supply less energy, the hydrogen atom will occupy the electron. Electron will be occupied at the hydrogen atom if you have supplied less energy than this, right? This is the minimum energy needed to eject an electron. This is the ionization energy. Actually, the ionization energy will be given by then the energy gap. The energy gap between the ionization energy will be given by then the energy gap between the n equals infinity and the n equals 1. So E infinity minus E1, that energy gap will give you the ionization energy of the hydrogen atom. Right? This energy gap will give you the ionization energy of the hydrogen atom. Actually, that is responsible for that energy gap is same as the energy gap of this transition. This energy gap is same as the energy gap of this transition. What is this transition? This is the highest energy transition of Lyman series. When electron is coming from n equals infinity to n equals 1, that is the highest energy transition of Lyman series. That also carries the same energy gap. N infinity to n equals 1. Right? So actually, the ionization energy of the hydrogen atom is actually given by the Lyman's greatest energy transition. Lyman's greatest energy transition is with the same energy gap as the ionization energy of the hydrogen atom. Right? So that if you know the energies of the infinite energy level and the first energy level, if you know the energies of the infinite energy level and the first energy level of the hydrogen's energy level diagram, then we can come up with the ionization energy of the hydrogen atom. So in this case, the ionization energy of the hydrogen atom is 0 minus 1312. That means the ionization energy of the hydrogen atom is 1312 kilojoules mole, 1312 kilojoules mole. This is the ionization energy. That gap. Right now? So if the energy level diagram is given, you should be able to come up with the ionization energy of that hydrogen atom. Right? What if they have given you the spectrum? What happens if they have given you the spectrum instead of the energy level diagram? If they have given you the spectrum, how to come up with the ionization energy? You should know that. To come up with the ionization energy if the spectrum is given. How to come up with that? Yes? Anyone? Give me a good answer. How to calculate or how to come up with the ionization energy if the spectrum is given? Anyone? Chris? Any idea? No idea. So I had told you that the ionization energy is responsible for the highest energy transition of the Lyman series. So that means this last line This last line, anyway the last line appears. The last line appears at the spectrum. The last line appearing at the spectrum. That is the highest energy line of the Lyman series. The last line. The last line of the Lyman series. The last line of the Lyman series gives you the, that is actually the highest energy line of the Lyman series. That will give you the ionization energy. If you know the frequency here, if you know the frequency here, if you know the frequency of the last energy line of the Lyman series, you can apply the E is equal to h mu. That will give you the energy of the photon corresponds to this, that last line. That will be your ionization energy. That will be your ionization energy. Right? So you can use the last line, the highest energy line of the Lyman series to come up with the ionization energy of the hydrogen atom. Right? Such a question can be asked by giving you the spectrum. That is how we are to find the ionization using the spectrum. If the energy level diagram is given, very easy. Just this energy gap, 1 to infinity. But if the spectrum is given, what you need to consider is the last line, the highest energy line of the Lyman series, and take that value, take its mu value, frequency value, or if it is given in lambdas, if the spectrum is given in terms of wavelength, you just take the wavelength of the last line of the Lyman series, the highest energy line of the Lyman series, then come up with the E is equal to HCO lambda. That will give you the, right, that will give you the ionization energy. Right? That is the idea. That is how we are supposed to come up with the ionization energy when the spectrum is given. Right? Okay? Right. Let's write this stuff, right? Let's write this stuff there, right? Let's write. See, it is said like this. The point says, the ionization energy of hydrogen atom, the minimum energy needed to supply to eject an electron from hydrogen atom is given by, those things are there in your note. Just write the stuff. From that, let's continue with red color. Continue with red color. Continue with red color. Energy gap between n equals 1 and n equals infinity energy levels. Energy gap between n equals 1 and n equals infinity energy levels. Just continue the statement, right, in red color. Energy gap between n equals 1 and n equals infinity energy levels. Right? Continue that thing, continue to the same thing with the normal color. So it relates to, right? Just write this, right? So it relates to n equals infinity to n equals 1. It relates to n equals infinity to n equals 1. You can write it even in red color. N equals infinity to n equals 1. Come to the normal color. Transition. N equals infinity to n equals 1. Transition. And so that it relates to n equals infinity to n equals 1 transition, and so that the, come to the red color and write, highest energy, and so that the highest energy within brackets, just continue the statement in red color, highest energy within brackets, lowest lambda, highest mu, within brackets, lowest lambda, highest mu. Highest energy means lowest lambda, right? Highest energy means lowest lambda, inverse relationship. Highest energy means highest mu, relationship. Right? Okay. Highest energy within brackets, lowest lambda slash highest mu, close the brackets. Line in Lyman series. Line in Lyman series. Right now? Okay. So we can write these relationships then. Right. Let's write the, let's come up with some pictures. about the ionization energy. Right? If energy level diagram is given, if energy level diagram is given, right, like this, just draw with me, Lamai. Just draw with me. We have discussed the ideas, so what we need to do is actually just come up with the node, right? Complete the node, right? This value is 0, 1, 3, 1, 2. These values are given in kilojoules mole, right? So you can write the ionization energy as the energy gap between these two. Right? Energy gap between those two. This is ionization. Just releasing the electron from here to here. Right? You can take the energy gap between the two. Right? The energy gap here. Delta E. So that is E infinity to E0. E1, sorry, E1. So E infinity 0. E1 value is minus 1312. So you will come up with 1312 kilojoules mole. Right? So just complete this off, right? This thing. If the energy level diagram is given, this is how you're supposed to come up with the ionization energy. Just take the, sorry, it is infinity, right? Just take the n equals 1 and n equals infinity. Just take those two. That gap will give you the ionization energy. Now, when taking a gap, always deduct the lower value from the higher value. The higher value minus the lower value. Take like that when taking gap in these pictures, right? Higher value minus the lower value. Take that as the gap, right? Right, when the energy diagram is given, you can copy the ionization energy like that. What if they have given you the spectrum? If they have given you the spectrum, just write that as well. If they have given you the spectrum, if spectrum is given, right? If spectrum of lines is given actually, lines will be appearing like this now. Ultimately the lines get overlapped now when going towards the higher energy region. The lines get overlapped now, right? Lines get overlapped now. So this is the Lyman. Just take the Lyman series. Just take the Lyman series. This is the last line, right? That is the last line. Just take the last line. No need to look at whether the frequency is towards each side or that side, right? Always the lines ultimately get overlapped, right? Towards the higher energy region. Towards the higher energy region, the lines will get overlapped. So that is the last line. That is the last line, right? So first line and second line have a greater gap. Like that, the gaps will decrease when the energy is increasing, right? Towards the energy increasing direction. So this is the last line. No need of mentioning here towards which direction the things are increasing. By just looking at the spectrum, you should able to come up with where the first line and where the last line. This is the first line. This is the last line. Going towards the higher lines, the energy will increase, right? This is the last line. Just take the last line of Lyman series. That is the idea. Just take the last line of Lyman series. Right? So you can come up with the ionization engine. So the ionization energy will be equal to, right? Ionization will be equal to energy of this energy photon. Energy of this energy photon. That is h mu. Energy of this energy photon related to this energy photon. Or the energy can be represented in terms of lambdas as well. So spectrum can be drawn in terms of lambdas as well. If in terms of lambdas the spectrum is given, it is HCO lambda. If the spectrum is given in frequencies, just take the frequency of this thing and multiply with h. That will give the ionization energy, range of that photon. Below the last line. If the spectrum is given in lambdas, just take the lambda of this last line and apply to the here. That will give you the range of the photon. We are responsible for that last line. That is your ionization energy. Right now? Okay. So here, this is the highest mu. Highest mu. This is the lowest of Lyman. Lowest lambda of Lyman. Lowest lambda means highest energy. Highest frequency of Lyman or lowest lambda of Lyman. Right now? Okay. Just write the stuff, Lamai. Just write the stuff. Here mu highest is the highest frequency. In Lyman series. Lambda lowest is the lowest frequency, sorry, lowest wavelength. Again, the last line. Last line means the highest energy line, right? Last line means the highest energy line. First line means the lowest energy line for any given series, right? In Lyman series. Right now? Just complete the stuff, Lyman. That is all about the ionization energy. How to find the ionization energy when the linear diagram or the spectrum is given. just take the Lyman series from the spectrum and consider the last line of the Lyman series, the highest energy line. Then take those values and apply to the E equals h mu or the E equals h c o lambda. That will give you the ionization energy. Okay. This is h mu, highest of Lyman. This is HCO lambda, lowest of Lyman. Lambda should be the lowest of Lyman. Okay. Lowest lambda means highest energy, right? Energy and lambda is with kind of a inverse shape. Right now? I'll send you a picture here, Lamai, for this one as well, right? So you can complete the note, right? Let's go to the next point. Let's come up with the next point here at the next page. Right now, okay. Next point. It says the single electronic systems will also give atomic emission spectra like hydrogen atomic spectrum. The single electronic system will also give atomic emission spectra like hydrogen. Right. Okay. Right. Sounds okay. Right. So it says the single electronic systems. Next page. Right? Let's go to the next page. It says single electronic systems will also give you the emission spectrum like hydrogen atom. That is what it says, right? See, what is the idea there? First of all, what are these single electronic systems? What are these single electronic systems? Single electronic systems. Now, single electronic systems means the species with only one electron. The species with only one electron. See, hydrogen is such. Hydrogen is such a situation. Hydrogen atom. Only one electron is there. The helium atom, it is with two electrons. When it comes to helium plus ion, helium is with two electrons. Helium plus means you have released one electron, so only one electron is remaining. Helium plus is also a single electronic system. When it comes to lithium 2 plus, it is also a single electron system. So lithium is your third atom. So releasing two electrons will give you the lithium 2 plus. It is also a single electron system. Right? What they have observed is all the single electron systems are with similar patterns. Like in the hydrogen emission spectrum. All the single electron systems gives you the same kind of patterns what you have seen with the hydrogen emission spectrum. So it's like this. So if the hydrogens n equals 1 line series appears like this, hydrogens n equals 1 series, if the hydrogens n equals 1 series appears like this, let's consider n equals 1 series. Right? For the helium plus, as well as for the lithium 2 plus, same kind of pattern can be observed. What is the pattern? Basically, the pattern is going towards the higher energy region, the spectral lines become closer. That pattern is also with the heliums. As well as with the lithium. So similar pattern is observed with all the single electron systems. But remember, these are not identical. These are not identical. Similar pattern is there going towards higher frequencies, higher energy regions, right? The lines become closer to each other. Similar pattern is there, but not identical. Not the same. Not the same. See, the first line appears here. If this is according to frequency, the frequency is here. But for this one, the first line frequency is greater than that. For this line, the first line frequency is much more greater than that. Right? So, similar pattern, but not identical. Similar pattern, but not identical. Remember that. If those are identical, you should be able to superimpose these things. Superimpose means you should be able to, right, take this one and put it here, and you won't see any kind of a change there. That is what we meant by superimpose. But if these guys are identical, you should be able to superimpose this. But that is not what happens. So all of these spectrums are with similar pattern but not identical, right? Get the idea. So you can draw this one, and I'll write the thing as well, right? These are with similar pattern but the most important stuff is not identical. Not identical. Not the same, right? Not the same. Right? So we'll write the reasons why we are saying so. Not identical means the wavelengths or the frequencies appearing with the lines are not the same. Even though you see the similar pattern going towards a higher energy region, the wavelengths becomes closer, the lines becomes closer, the similar pattern is observed, but not identical. The wavelengths are not the same, or the frequencies are not the same with all spectrum, all the spectrum, right? Wavelengths, frequencies of spectral lines differ that of hydrogen spectrum. Lamai, that is actually due to the nuclear charge, right? This is due to actually nuclear charge. So basically, the nuclear charge is greater here. So electron is greatly attracted to the nucleus. Electron is greatly attracted to the nucleus. So to excite that thing, to excite such electrons, you need great energy. You need great energy. That is why the patterns are always coming towards the high energy region when the number of positive charges at the nucleus is high. When the number of positive charges at the nucleus, the protons are high, the electrons are strongly bound to the nucleus. So that you need to give some great energies. So energy levels are with some greater values, right? When it comes to great number of protons in your nucleus. That is why the energy values are actually at the higher side compared to the hydrogen when you have more protons. That is the idea, right? no need to know that much of things, right? But anyway, remember that the frequencies at the wavelengths appearing with the lines are not the same, even though following the same pattern, right? Okay, let's complete the stuff. Right? Right, that is all you should know about the high definition spectrum. Right, is all you should know about the stuff. Let's do some one or two questions regarding this one. Means some numerical questions, calculations. Right, I'll do one or two. So two questions are there in your tute. I'll do one or two of those, right? And you have more questions with your workbook. I wish you got the workbook, right? And for the Deshana, I will send you the workbook, right? So you just now registered, so we'll send you the workbook, and in our workbook we have more questions. Right? Do those questions. I'll do one or two questions of this book, right? This tute. Then you can do more questions with the workbook. So for the workbook questions, I'll send you the answers. We are not supposed to discuss all the questions at the workbook, but we'll send you the answers. If you have any doubts with those answers, and if you are not getting any other answers which I send you, right? Then you can ask them at the class, right? Okay, that is how we go with the workbook. Right, okay, I'll do one or two questions appearing at the tute, right, to have some idea how the questions will be asked with the numerical questions, right? So then you can do the workbook at home, right? Okay, this is complete now, this is clear now? So we can send a picture as well, right? Let's Lavan, just go to the question number 1. Just go to the question number 1. Quickly go to the question number 1. I'll solve that thing, but just read the question number 1 and see, and then get some idea about the question. We'll discuss the question number 1 and 2, right? Basically. Right. This picture will be sent to your WhatsApp, right? Okay. Let's come up with the next stuff, right? Now, do you have any questions regarding this thing up to here? These are all the theory stuff we are going to discuss today. Any one of you with any questions regarding the stuff so far? You can send to the chat box as well. Not really. Not yet. Okay. Right. If you have any questions, you can ask at the next class as well. So then we'll quickly do the calculation questions, right, to wind up the session, right? So I'll helping you to do some few calculations, right? Then you can complete the stuff at the workbook, right? So let's do the first one. Question number 1. What it says? Question number 1. It says the first line of Balmer series is at 656 nanometers wavelength. They have given you the wavelength as 656 nanometers. They are saying that is that is the wavelength of the first line of the Balmer series. This is the red colored line, right? And they are asking the energy gap between the two energy levels correspond to that line. The idea is this now. So they are saying what is this, right? So Balmer's first line means the electron is coming from n equals 3 to n equals 2. Balmer's first line, no? Balmer series lines means the electrons are coming towards n equals 2. Balmer series lines. Electrons are coming towards n equals 2. The first line means coming from the nearest high energy level. So this is the electronic transition response to the Balmer's first line. So if you are to take this as E3, take this as E2, what they are asking is the energy gap between these two. They are asking is the energy gap between these two. That is the idea of the question. They are asking us the energy gap between the two corresponding energy levels. This is what they are asking. Right now, if you take a clear picture of what they are asking, this is the Balmer's first, this is the electronic transient response Balmer's first line, right? They are asking the energy gap between the two corresponding energy levels, right? We can come up with that using what? So we know when electron is coming towards the low energy level, it will release its excess energy as a photon, as a energy photon. So the energy of the photon is actually equal to the energy gap between the corresponding energy levels. That is the idea. So we can write it as E photon is equal to delta E, the energy gap, where delta E is equal to E photon. Right, take it as delta E is equal to E photon. Both are same, isn't it? So energy of a photon can be represented in terms of wavelength, as they have given you the wavelength. As they have given you the wavelength here. They have given you the wavelength of the energy photon, 656 nanometers. So you need to come up with in the form of a wavelength. So in the form of wavelength, it is HCO lambda. HCO lambda. Photons energy in the form of wavelengths. So H is the Planck's constant. H is the Planck constant. It is 6.6 into 10 to power minus 34 joules per second. C means the speed of light, 3 into 10 to power 8 means minus 1. Lambda is the wavelength. It is 656. But nanometers. Keep it in mind, you need to substitute with the SI units. You need to substitute with the SI units. So SI unit is not the nanometers. SI unit is meters. So you have to need to substitute for the nano. Nano means 10 to the power minus 9. Nano means 10 to the power minus 9. Now I just see the last day's lesson. Just see the last day's lesson where we have discussed about solving these kind of stuff, right? 656 nanometers. Nano means 10 to the power minus 9 meters. That N carries 10 to the power minus 9 nanometers. Just simplify this stuff. When we are simplifying this stuff, right, you can take it like this. The values are like this. 6.6 is there, 10 to the power minus 34 is there, and 3 into 10 to the power 8 is there, and 656 can be taken as 660. No worries, Lamai. No worries. You can take this one as 660. Last day we have discussed about those things. Just go to that video again. Right? For two significant figures, that is okay. 656 can be taken as 660. The reason is mentioned in the last video. Just go to that quickly, right? Just go to that. Right? So, know that it is very easy to cancel off these stuff, right? This will be then 100, right? That will be then 100. So remaining stuff is 3 into, just you have, this will be cancelled off, right? So 10 to the power 9 is 19. This will become 10 to the power 15, right? These two will cancel off. So it is 10 to the power minus 19. So the answer is 3 into 10 to the power minus 19, right? You can come up with the SI unit. As you are doing substitution with the SI unit, you can just put the SI unit as the unit of the answer. As the unit of the answer, you can just put the SI unit. No need of cancelling the units, right? No need of cancelling the units. You can just put the answer in SI units as you are substituting with the SI units. When you done the substitution with the SI units, you can just put the answer in the SI units. The SI unit of energy is joules. SI unit of energy is joules. That is how we are supposed to come up with the answer, right? Okay, this is how we do the simplification, right? Okay, I'll come up with the next question as well. So we'll send you the recording as well, so you can go through this stuff, right? So I'm just helping you to solve the questions in your workbook, right? So we'll do another one, the second question as well. Right. Okay. Now definitely go through the last video lesson, right? That is, we have discussed how to solve these things, right? How to apply this equation correctly, right? What are the marking points and the things were discussed, right? So let's come up with the second stuff, right? Second one. So for the second question, they are with kind of atom. They are with kind of atom with some energy levels. They are with kind of atom with some energy level, right? Some energy levels are there, right? So I'll draw the energy levels, right? Right. So this E4, E3, these are the energy levels given in your atom at the question, right? So values are also given, minus 15 into 10 to the power 19. The C2 value is given as minus 10 into 10 to the power 19. E3 is given as minus 5 into 10 to the power minus 19. E4 is given as minus 1 into 10 to the power minus 19. Right? Okay. So let's come up with the questions. First question, question A. It is about which kind of transition? Calculate the energy of the photon required to excite an electron from E2 to E3. You are supposed to excite an electron from E2 to E3. You have the electron here. You are supposed to excite that thing to here. You have electron at the E2, the Roman number 1. This is Roman number 1 stuff, right? At the Roman number 1, you have electron at the E2 and you are supposed to excite that into E3. So you are supposed to increase the energy of your electron. You are supposed to increase the energy of your electron, right? So actually towards this side the energy is increasing, right? Energy is increasing, right? So I can put it as energy increases, right? Okay. So you are supposed to increase the energy of your electron. When you are at a low energy level, you are with a low energy. When you are at a high energy level, you have the high energy. So when you are here, you have this amount of energy, minus 10. When you are here, you have minus 5. Minus 10 is lower than the minus 5, or the minus 5 is greater than the minus 10. So you are supposed to increase the energy by absorbing an electron. So some photon energy should be absorbed for that. E photon. So what they are asking? They are asking calculate the energy of the photon required to excite an electron from E2 to E1. They are asking the energy of this photon. So we can write, right? E photon is equal to delta E. Energy of the photon is equal to the energy gap between the transition, right? So they are asking what? They are asking the energy. Just the energy they are asking. So energy of the photon they are asking is equal to delta E. Delta is the energy gap. This energy gap, this gap. What is the gap? This minus this will give you the gap. So you can write it as minus 5 into 10 to the power minus 19 minus 10 into 10 to the power minus 19. That is the energy gap. It is minus, it becomes plus, minus 5 and plus 10. That is 5 into 10 to the power minus 19. Right now? That is the first question. Right? That is the first question. I'll do the second one as well as the final question. What is about the second one? They are asking the B question, question B. Sorry, this is the question A. This is the first one. E. What about the B? At the question B, they are writing, asking the question like this: calculate the wavelength of the photon which is required to excite an electron from E1 to E4. You are trying to excite an electron from E1 to E4. E1 to E4. This excitation is expected at the question B. For that as well, you need to provide an energy of a photon, energy of a photon. So for that again we can come up with the same relationship. But E photon is equal to delta E. Energy of the photon is equal to delta E, the energy gap between these two. Here they are asking about the wavelength. So the photon energy can be represented in terms of wavelengths. It is h co lambda in terms of wavelength. h co lambda in terms of wavelength, because they are asking the wavelength. Delta E means the energy gap. I'll take the gap directly. The gap between these two, minus 15 and plus 1. Sorry, minus 15 and minus 1. The gap between the minus 15 and minus 1. So it's like this, no? You have the minus 15. You have the minus 1. The gap is actually 14 units. Gap is 14 units, right? Minus 15 and minus 1 is there. Gap is 14 units. So 14 into minus 90. This is equal to 14 into minus 90 joules. So substitute the values here. HCO lambda. Right? I'll substitute it here. Right? So H means 6.6 into 10 to the power minus 34 joules seconds. C means 3 into 10 to the power 8 ms minus 1. Lambda, that is what they are looking at, lambda. That is equal to what? This number 14 into 10 to the minus 90. Right now? Okay? So with this we can subject the lambda. With this we can come with the lambda. Lambda is equal to, I'll do the simplification here. If you take the lambda here, it will be like 6.6. Just taking lambda here, right? Lambda here, the cross multiplication, right? Lambda here, this comes here, right? 6.6 into 10 to the power minus 34 is there. So 3 into 10 to the power 8 is there, over 14 into 10 to the power minus 19 is there. Just simplify the stuff, right? As a lambda. This is the lambda, right? So 6.6 into 3 will give you 19.8 divided by 14. 19.8. 3419 will cancel off as 25. 25 into 8 10 to the power how much? 25 to 8 10 to the power 17 minus 17, no? It is 34 15, no? 15, right? Then 8 comes, right? Minus 7. So this value is actually 1 point, right? You are in 48, right? This will be like into 10 to the power minus 7. One point. I'll just do the calculation stuff, right? 1.41, right, into 10 to the power 7. So lambda is 1.41 into 10 to the power minus 7. So answer comes with SI units. Remember that. As you have done the substitution with the SI units, the answer comes with the SI units, the meters. As you have done the substitution with the SI units, answer comes with the meters. So that is the idea. That is the idea. Right now? So that is how we are supposed to solve these kind of questions regarding these energy levels and the electronic transitions and the involvement of photons. Right now? So that is the idea. So you can copy the stuff, or even I will send you the photographs of these things, right? Okay, this is how we are supposed to solve these kind of things. Right now? So we'll wind up at this stage, right? We'll stop with this one. Then we'll yeah, I'll prefer you some work. So basically now all the work given in the workbook can be done now regarding the hydrogen spectrum. All the work, all the questions regarding hydrogen spectrum can be done now, because all the theories have been discussed with the hydrogen spectrum. Right? Do the next question as well, the third question, and the workbook questions. Right? I'll send you the answers for the workbook questions. Right? Okay. Then we'll wind up at this thing. Do you have any questions, Lamai, first of all, before winding up? If you have any questions, I can give some explanations. If not, we can stop from here. Yes? Deshana, do you have any questions? No doubts, it's clear, no? Right, then the Shashabdra? No worries. Right. Okay, then we'll stop from here. Then good night then. See you next week. Goodbye.